Hi, my name is Alexander Munoz, and I'm going to be talking to you today about the inhomogeneous diffusion equation. So behind me right here, we have the regular diffusion equation that we've seen before. But the important part about this case are the boundary conditions. So let's take a look at those over here. U of 0, comma t is typically equal to 0 in the cases we've seen before. But let's say it's equal to some constant. Call it U1. And let's say U of L comma t is equal to a different constant. It's called U2. And we'll also need some initial conditions for this problem. So let's say U of x comma 0 is equal to some equation f of x. Okay, so let's try to visualize what we're actually looking at right now. So let's start by plotting U1 and U2 here on the y-axis. We know that at U, for all time at x equals 0, U will be equal to U1. So here's x equals 0, comma U1. And we know for all time at x equals L, U will be equal to U2. So that's this point here. And these work for all time. At the initial condition, these 2 points will be connected by the function, by our initial condition, the function f of x. So let's say that looks like this. But over time, because there's no flux between the boundaries, this function will degenerate to be linear connecting these 2 points. And this function will be time independent and will work for very large values of time. So we can say that the limit as time approaches infinity of U of xt is equal to some time independent function. Let's call it U sub s. And this function, this U sub s is only a function of x, not of t, because it's time independent. So we also know that U sub s will work as a solution for our diffusion equation, as well as a solution for these 2 boundary conditions, because they're time independent. However, it will not work for our initial condition, which is time dependent. So let's start by plugging U sub s into the diffusion equation, since we know it'll work. The partial derivative with respect to time of U sub s equals d times the partial derivative with respect to x twice of U sub s. We know U sub s is time independent, so we can say that this immediately will go to 0. The partial derivative of anything that doesn't have a function of time in it with respect to time will be 0. We can divide both sides by d to get rid of this variable here, and we're left with the second partial derivative with respect to x of U sub s equals 0. So this is just a ordinary partial differential equation. We can write it like this, because everything only has x as a variable right now, is equal to 0. We know how to solve this equation here from the first module. You just integrate twice on both sides, and you're left with U sub s is of the form a plus bx. So how are we going to find these a's and b's? Well, we know that our U sub s also works for the 2 boundary values. So let's plug those in and see what we get. Let's start with x equals 0. U sub s equals a plus b times 0 gives us a. Okay? U sub s equals a plus b times L equals a plus BL. So now we know that U sub s at x equals 0, this is equal to U1, and at x equals L is equal to U2. So from here what we want to do is we want to solve for a and b, so that we can plug values of U1 and U2 back into this equation we have for US. So we know right off the bat U1 is equal to a. So now we can plug that in here. U1 plus BL equals U2. And now I want to solve for b in terms of u1, u2, and l. So that's easy, it's just algebra. B equals u2 minus u1 over l. All right, let's plug those back into our equation for a and b. We have us equals u1 plus u2 minus u1 over l times x. Okay, so this works for very large values of time, but we haven't satisfied our initial condition yet. So we're actually going to need another equation to solve for this initial condition here. And we're going to say that u of xt is the sum of our long-time solution, u sub s, plus an equation that satisfies the initial conditions, u bar. So let's plug these into our diffusion equation. We know they'll work for the diffusion equation, and let's see what happens. The partial derivative with respect to time of u sub s plus u bar equals the second partial derivative with respect to x of u sub s plus u bar. So we can just say that the derivative of a sum is the sum of the derivatives, and say the partial derivative with respect to time of u sub s plus partial derivative with respect to time of u bar equals second partial derivative with respect to x of u sub s plus second partial derivative with respect to x of u bar. We know that u sub s is time independent again, so that partial derivative goes to 0. We showed earlier that the second partial derivative with respect to x of u sub s equals 0. That's over here. Okay, so that goes to 0. So we're left with the equation, the first partial derivative with respect to time of u bar equals second partial derivative with respect to x of u bar. So it seems like we've done a lot of work, but we have an equation that's very similar to what we started with. So what's up? Well, our boundary values have actually changed because we've now satisfied them over here. So let's take a look at how that looks. Let's plug in for u0 of t. We know that's equal to our stable us at 0 plus u bar at 0t. And we know all of this is equal to u1. We also know that us of 0 is equal to u1. We showed that right here. So this is equal to u1 plus u bar of 0t is equal to u1. We just can cancel these on both sides, and we're left with u bar at 0t equals 0. Let's do the same thing for ul of t. ul of t equals us of l plus u bar of l comma t, and that's all equal to u2. Once again, u sub s of l is equal to u2. We showed that earlier, so we can just cancel those off on both sides, and we're left with u bar of l comma t equals 0. So now we have two homogeneous boundary conditions. These two up here were equal to constants, so they're inhomogeneous. Now they're equal to 0, so they're homogeneous. The last thing we have to solve for is our initial conditions. So we have u of x0, x comma 0, equals us of x plus u bar of x comma 0, and all that is equal to f of x. So what we're going to do is we're going to subtract the log time solution for this initial condition from both sides. And we're left with u bar of x comma 0 is equal to f of x minus u sub s x. Both of these are just functions of x, f of x and u sub x of x. So we can just call this difference here g of x. So now what we're left with is we have first our equation for u sub s, which we solved for over here. And then we also have a partial differential diffusion equation for u bar. And we have two homogeneous boundary conditions. And then we also have a normal looking initial value condition. So that's pretty much it to make the inhomogeneous diffusion equation into a homogeneous problem added with a stable solution for long times. Thank you for watching.